All right. We're looking at an example using OGS. And so how many ways can you roll a total of 8 using one dice from 1 to 2, one dice from 1 to 4, and a standard dice? So standard dice is from 1 to 6. So for these dices, we can count um, the number of ways that we can get a number for each dice. So let's start with the dice from 1 to 2. So let's denote that as dice 1. Uh, denote this as dice 1. Dice 1, dice 2, and dice 3. So dice 1, the OGF of dice 1. So OGF, that's ordinary generating function of OGF of D1 is equal to, well, how many ways to roll 0? You can't roll 0 with dice ranging from 1 to 2, so 0. How many times can you roll 1 within one roll? Um, you can only roll one once, right? Because they said how many ways can you roll a total of 8 using one roll from each of these. So we can look at each dice that are being rolled once. So the dice 1 being rolled once, it can only achieve n equals to 1. Um, n equals to 1 can be achieved once, right? Because they can roll 1 or 2. And so 2 can also be rolled once. But this n equals 2. And then n equals to 3, a dice ranging from 1 to 2 cannot, get the number 3 on it. So it's gonna be 0. Same with 4, 5, 6, dot, dot, dot. And so that's going to be OGF of dice 1, which is also equal to, that these are coefficients of the x to the power of n, starting from n equals to 0. And so we have 0 times x to the power of 0, plus 1 times x to the power of 1, plus 2 times x to the power of 2. And then the rest are going to be zeros, right? That's also equal to x plus 2x. Oh, I'm sorry. There's not 2. It's a 1. Because we have the coefficient 1 for n equals to 2. So it's gonna be 1x squared. So it's gonna be equal to x plus x squared. All right, and so we do the same thing for OGF of dice 2. OGF of dice 2 is gonna be the same thing, but n equals to 3 and 4 can be also achieved. So yeah, 0, 0, comma 1, comma 1, comma 1, comma 1, because it can roll 1, it can roll 2, it can roll 3, it can roll 4. All of them once within one die roll, and the rest is 0. Cannot roll 5 or 6 or something greater, and it can't roll 0 either because there's no 0 on the dice. All right, and this is going to be equal to, again, x plus x squared plus x3 plus x4. All right, and OGF of dice 3 is equal to the same thing. So 1, 2, 3, 4, 5, 6, and then zeros. Plus x2, x3, x4, x5, x6. And so now we have the 3 OGFs, as I said in the last video, that to find the OGF of a problem, like a function of the entire problem, in this case, the function a of n is going to be equal to the number of ways you can roll using all 3 dice at once, all 3 of these dice at once for one coin roll, one dice roll from each. Can be that OGF is going to be equal to the OGF of each individual situation multiplied together. And so in this case, we can just multiply each of these together, and we get that the final OGF is going to be equal to this. Um, copy this. Um, times this times this. And so now we have the OGF of A of n. Um, and now let's look at your question. They're asking for how many ways you can roll a total of 8. And so when you see the total of 8, that's n, right? Because our A of n is equal to the total, how many ways you can, A of n is the number of ways to roll a total of n using each of these dice. And so when they're asking for n is equal to 8, we have to find the coefficient of x to the power of 8. And so how do we find the coefficient of x power of 8 in this, big expansion? Well, in this case, it's not that complicated because it's a, relatively like small multiplication. Like it's not hard to see which cases we can achieve x power of 8. Well, let's first simplify and factor out these x's, right? Because we can like re-express this as x power of 3 times 1 plus x times 1 plus x squared plus x cubed. Because we can take out x for each of these expressions. Because each of them are divisible by x. Times 1 plus x squared plus x power of 3 plus x power of 4 plus x power of 5. All right, so then if we're trying to find the coefficient of x power of 8, then that also means that we're trying to find like if we're trying to find you know some question mark x power of 8 in this entire expression, that's also meaning that we're finding x power of 5 in this expression, right? Because you can multiply by x power of 3, which would if you multiply, then you add the exponents, and so that will get you to x power of 8. So if we find the x power of 5 coefficient in here, that will also get our answer. So that makes it more simple. So how do we find the coefficient of x power of 5 in this big expansion? Let's ignore the x power of 3 for now. So x power of 5, how do we get combinations of x power of 5? Well, we can literally count, right? In this case, it's really easy because, all right, one case is if you have 1 times 1 times x power of 5. That's one case. 1 times 1 times x power of 5. And we can go next, right? Next, like there's no other way to use that, right? So we can use this, see how we can use this term in this instance, this dice 3, that we can get x power 5. Well, there's two ways, right? You can have 1 times x power 4, or you can have x times 1 times x power 4. And so that's 3 instances, right? And that's it, right? Because if you have x power 3 times x, that's going to be x to the power 5. I mean x power 6, because you're going to have x power 4 times x to the power of 1 times x to the power of 1. That's going to add up to x power 6. And so our next term that we can check is x to the power of 3. How can this get to x to the power of 5? Well, there's two ways. You can either have x to the power of 3 times this times 1. So I'm gonna write that out. You have the 1 from this first term times x cubed, squared times x power of 3. That's gonna get you x power of 5, right? All right, that's one instance. And then the next instance is if you have x and x, right? X times x times x to the power of 3 is x to the power of 5. So you have x times x times x to the power of 3. All right, and so that's going to be all for x power of 3, because if you multiply by anything else, it's going to give you more than x to the power of 5. And so we're done with that. And so this had one instance, this had two instances, this had also two instances. And so we check for x to the power of 2. So x to the power of 2, how do we get this to x to the power of 5? All right, let's pair x to the power of 2 with this first. So 1 times what times x to the power of 2 can get us x to the power of 5. Like what from the middle term? Because ultimately for every term in this expanded sequence, we're gonna have one term from each one. That's why I'm doing casework um for each of these dice. And so in this case, how do you get to x to the power of 5? We the only possibility is x to the power of 3. So we have x to the power of 3. And so that's all for x to the power of 2. That's one instance. But wait, actually, I meant one instance for x to the power of 2 being the last term and then taking the 1 out. But let's try x now, right? So what if you have x times something times x to the power of 2? What is that something? Well, we need x2, right? And that's one instance. So that's only one possibility to get x to the power of 5. And so now we evaluated that there's only one way to get that. And so let's try x now. We have x as the last term times something times something. Let's try 1. 1 times x. You need x4, but there's no x4 in this, so that doesn't work. So let's try x. If you have x times x as x to the power of 2, how do you get x to the power of 2 times something equals to x to the power of 5? You need x to the power of 3, and we do have one of those, so that's going to be 1. So that's going to be one instance. And so this is going to have one instance, and you guessed it, if you had x, if you used 1 for that last that last dice, then the OGF for the last dice, you have 1. You have 1 times x to the power of 3. And when I say the OGF of the last dice, that's ignoring the x to the power, the extra x that we removed. But you have 1 from the last one, x to the power of 3 from the second one. And you have times x. And this is the maximum amount of x that you can get. But notice that this is x to the power of 4, so we can never get x to the power of 5 with 1 as the last term of the last dice OGF sequence. And so these are all our possibilities, and so if we add them together, we get 8 ways. That's our answer. And that's an example of how to solve OGF using, solve this problem, combinatorics problem with 3 parts using OGFs. It's pretty cool, right? Yeah. All right, that's it. Hope you join me for the next example where we're gonna go through a more eye-opening problem using OGFs, because we're gonna use binomial theorem and we're gonna use geometric sums. All right, bye.